Good morning.
Good morning, dear.
Good morning.
Good morning, dear.
Good morning.
Morning, Shai. Okay, ladies. Any questions? Does anybody have any questions yet? So yesterday we talked off scattering, which we mean, yes, okay, just say was okay, as a way of saying dispersion. Okay, which mainly as okay happens. Here, this for instance, there was a tissue boundary. We had a sound wave hitting the tissue. And what media okay was going to be in this case, yes, okay, scattering or dispersion was going to be some of this energy carried by the sound wave here is going to get dispersed or spread out. Clear? The main thing we said was, which is pretty much okay, as we can say, okay, the main factor is that okay, as it is going to be as okay directly proportional to frequency. Which means to me yes, okay, greater frequency will lead to more scattering. I mean, you can say the scattering of I was going to be as okay, the dispersion of the sound energy. Right, okay. And vice versa. Is that clear? And primarily, yes, okay, we can say mainly as okay due to scattering being as okay directly proportional to frequency. That's why it's okay. Frequency is one of the factors that lead to attenuation. Mainly as okay due to scattering. We also said, and that's going to be as okay important, that the lung tissue has a great amount of scattering. And what you guys will see later today is okay, that lung tissue is mainly as okay going to be as okay the tissue having the highest attenuation. American mainly says okay that is primarily as okay due to scattering. Okay. Okay. Now goes in scattering, yes, okay, we had okay as a subtype of scattering. Okay, I mean that's okay, just recall that, yes, okay. Rarely scattering. Now usually it's okay, because when we say scattering, we can say it's okay, just going to be as okay. A random dispersion of the sound energy. Clear? Whereas when we say rarely scattering, there's going to be as okay, it's going to be scattering, which we mean, yes, okay, or said was dispersion of, that's okay, the sound energy at a tissue boundary. Okay. But what's the difference between, yes, okay, a regular scattering and a rarely scattering is that this is going to be, yes, okay, we can say an even and equal scattering in all directions. Clear? Okay. Which may lure mean that, okay, yes, if a sound wave, yes, okay, when a sound wave, yes, okay, hits a tissue boundary, there is going to be scattering, but we call that just okay. Rarely scattering is that is an even. And we can see it's okay, equal amount of energy is okay being dispersed in all directions. Did that make sense? So that kind of scattering is okay, that's what we call Rayleigh scattering. Okay, so we can say it's okay, equal and even or even amount of energy being scattered in all directions. That will be what we call a Rayleigh scattering. And this kind of scattering here is okay, mainly is going to be seen as okay when the sound wave hits red blood cells. Mainly because of, yes, okay, we can say it's okay, the very, very, very small size of the RBC. Did you guys get that?
Can you repeat that for me?
Rayleigh scattering is mainly as okay going to happen when we can say it's okay, a sound wave hits a red blood cell. That's when we will have Rayleigh scattering. And why? Mainly it's okay because the small size of your red blood cells. Okay, so the thing about is okay, Rayleigh scattering versus regular scattering is that okay, as a regular scattering is going to be as okay, we can say not even, that may be as okay, you can say in this case, yes, okay. Greater amount of energy traveling this way, lesser this way, something intermediate this way. Okay, and it's not going to as okay be in all directions. We can say as okay inside as okay, we may not even have sound energy be scattered in this area here. So here is okay, we can say there is, and maybe it's okay. No scattering. Okay, which is going to just okay be different when we talk Rayleigh scattering, because I said it's going to be an equal and even scattering, which means is okay, we'll say whatever just okay, dispersion of the sound energy. And it's not going to just okay, just happen in one direction or another direction or another direction. It's going to be as okay happening in all directions. And we can say it's okay, the amount of energy that is being dispersed in each direction is going to be the same. That is what we'll call Rayleigh scattering. Okay, now girls, please keep in mind, because the term here is okay in all directions, can also as okay be replaced by what we call as okay omnidirectional. Which mainly as okay means the same as in all directions. So we can in that case say as okay, the Rayleigh scattering is going to be as okay even and equal scattering of sound energy or any energy, or an omnidirectional even and equal scattering of energy. Where the word omnidirection means it's okay, just for me, it's okay in all directions. Where the amount of energy is okay traveling this way is going to be equal to the amount of energy traveling this way, which is equal to the amount of energy traveling this way, this way, this way, this way, this way, this way. Did you girls get that?
Yes.
Now, another important thing is going to be as okay is the relationship. So to make it simple, girls, to make it simple, yes, okay, mainly because okay, we can say it's okay that Rayleigh scattering, yes, okay. Generally, yes, okay, just is a form of scattering. Where we say the scattering itself, yes, okay, was simply as okay, directly proportional to the frequency. So since Rayleigh scattering is a form of scattering, yes, okay, that is also going to be, yes, okay, directly proportional to the frequency. Will be, yes, okay, directly proportional to frequency. But the difference between, yes, okay, regular scattering and Rayleigh scattering is that, okay, yes, and that's mainly because, yes, okay, because we said the Rayleigh scattering here was omnidirectional. Or we can say, okay, was dispersion in all directions. That's going to be as okay directly proportional to the frequency raised to the power 4. Which mainly will mean that okay, whatever your frequency value is, we can say that's okay, we had a frequency of, let's say, it's okay, 3 megahertz. Okay. That will mainly is okay, we'll say it's okay, what's going to be, it's okay, the value of your Rayleigh scattering, that's going to be as okay, this, sorry, 3 megahertz here, sorry. Let me just do it this way. We can say it's okay, this 3 megahertz. And when we say it's okay, raised to the power 4, what does that mean? That does not mean that you multiply 3 by 4, because in that case, that's okay, your answer would have been 12. That is not what any number raised to the power 4 means. That would mainly mean that, okay, actually in this case, it will multiply 3 by itself 4 times. So you can say, okay, 3 times 3 is 9. Times 3 is 27. Okay, times 3 is 84. So that will be as okay, we can say it's okay, the value of your Rayleigh scattering. Did that make sense? So this relationship between as okay, Rayleigh scattering and frequency, well, okay, what it means to be directly proportional is that okay, as the greater your frequency, more Rayleigh scattering. You can say that's okay. Lower frequency, less Rayleigh scattering. Okay, but not directly proportional, because okay, it is going to be as okay it's going to be as okay the value of the frequency times time in itself 4 times will be as okay equal to as okay the amount of Rayleigh scattering. Did you girls get that?
Yeah.
Okay. Whereas okay, as far as okay, regular scattering and frequency was concerned, it is straightforward. We can say it's okay. Scattering is mainly as okay, just directly proportional to the frequency. Where we then also say that's okay. Frequency was okay as directly proportional to attenuation. Which mainly means as okay. Greater frequency, more scattering, more attenuation. Or the opposite way, we can say as okay. A lower frequency will lead to lesser scattering. Lesser scattering will okay mean lesser attenuation. Yeah, but here it's okay. In this case, here we can mainly say it's okay that there is no squaring, no tripling, or cubing, or it's okay, or squimes, or so exponent to your frequency or scattering. It's directly. Whereas for Rayleigh scattering is going to be as okay. The value of frequency is going to just okay, we multiply by itself 4 times to determine how much Rayleigh scattering there's going to be. Any questions? Any questions, ladies?
No.
See. So did everybody get that? Good. Now we just have one last process that, okay, yes, as you could say, it's okay, contribute to attenuation. And that last process is absorption. And what we mean is, okay, mean here is going to be, we can say, okay, absorption of, well, okay, since we use sound energy. Okay, we can mean says, okay, that's going to be, it's okay, the energy that is going to be, it's okay, a form of energy that's going to be absorbed. What does that mean? What do we mean by absorption of energy? We can mainly say, okay, if this here is okay, was your transducer. Clear? We can say, it's okay, this is a tissue. Now, what is going to happen is that, okay, as this transducer here is, okay, it sends out a sound wave. Yesterday, I already said that, okay, as some of that energy, as it hits this tissue, is going to, as okay, return back. That was what we called reflection. We just today, yes, okay, and yesterday also discussed, yes, okay, some energy is going to get scattered. So that is the scattered energy. Well, what mainly is going to happen is we can see, it's okay, that this sound wave is okay, that was produced by the transducer, is okay, will also, some of it will travel through the tissue. Because it's okay, needs to, it's okay, get to the other end. And what mainly is going to happen as this sound wave, yes, okay, travels through this tissue, the tissue will take out some of the energy. Or we can mainly say, okay, it's going to absorb the sound energy into the tissue. Did that make sense? So what mainly happens is, okay, as a result of that is that, okay, yes, the amount of energy that, okay, ends up at the other side here. We can just say, okay, this was 1. We can label this one here as 2. Sorry. 2. The remaining can say, it's okay, that the amount of energy in 1 is going to be greater than the amount of energy in 2. Clear? Now, what we mainly said here was that, okay, yes, is going to be, yes, okay, sound energy that is going to, yes, okay, be absorbed by the tissue. Okay, but there is, okay, as a general law of physics. We may talk about it later on in this chapter here. Although, yes, okay, your book discusses it in a later chapter, which we may just call as the law of conservation of energy. Okay. Where we mainly as where the last part of this law of conservation energy actually is states it that energy can change its form. And that's why it's mainly as is going to happen in this case. Because what we had to begin with was it was sound energy. Clear? As it just hits the tissue. And we can say it's it gets absorbed in the tissue. That some of the energy is carried by this sound wave here is going to be absorbed by the tissue. This absorbed energy actually is going to change its form from sound energy to heat energy. Is that clear? So we can mainly say that as this absorption of energy is one thing that it does is that it actually is leads to attenuation. It's a process that causes or contributes to attenuation. Because what was it that we mean by attenuation? That this initial energy here is going to be greater, and this is energy at the other side of the tissue. Right. Okay. That mainly as explains that as the amount of energy over here is lesser than what we had over here. But this energy that is was absorbed by the tissue is going to be converted from sound energy into heat energy. Clear? So this absorption is an example of both what we called acoustic propagation properties. Which mainly because as it was going to be as we could say the effect of the tissue upon the sound wave or sound. Clear? Because it was mainly going to be determined by the nature of the tissue. How much sound energy is going to be absorbed. And we can say the more sound energy is going to be absorbed by the tissue, or mainly causes that as a lesser amount of sound energy is with, and the other side here, which was an example of, you could say as the effect that this tissue here had upon the sound energy as it propagates through the tissues, which was an example of acoustic propagation property. Now, on the other hand, we also said that now when this sound energy is absorbed into the tissue, it is converted into heat energy. So that's why we mainly can say that absorption also is going to be leading to what we will call a biologic effect, or which we may later on call as bioeffects. Because what this heat energy here is going to lead to is we can say that will lead to we can say like a warming up, or in -16 is heating up of the tissues. Okay, which eventually is okay. If the heating or warming of the tissue is enough to affect the tissue, it can lead to just okay bio effect or biologic effects. Clear? Again, yes, okay, that is going to all be dependent upon, first of all, how much energy is being absorbed by the tissue. Clear? That would be as okay. You can say as okay, a contributing fact to as okay, leading to as okay, bio effect or biologic effects. Okay. The second thing is yes, okay, also going to was okay. How much change in its regular temperature is it that okay, as this tissue is going to be able to withstand without suffering? Or yes, okay, be affected in a extent that okay, as this amount of heat energy is okay, leads to bio effect or biologic effects. Is that clear? So absorption of energy is okay, will contribute to attenuation. Where we can say it's going to be as okay. That the effect that the tissue itself is okay had upon the sound energy. Okay, where absorption is okay was okay as an example of acoustic propagation property. But absorption is okay also contributes towards bio effect or biologic effects. Okay. As a matter of fact, girls, even yes, okay, this amount of that's okay, we can say it's okay. The sound energy that the transducer produces initially wasn't sound energy that actually is okay, is derived from electrical energy. So there's actually that's okay going to yes okay be some process going on in the transducer, which is converting this electrical energy here into sound energy. We still yes okay again yes okay confirm what we said in yes okay the law of conservation of energy. That is okay energy is mainly yes okay something that has the capacity or ability to change its form. Did that make sense? Now we have a living example in our rooms. Those of you who have turned lights on are right here behind me. What do you have? A light bulb, right? What does that run on?
Electricity.
Electricity, which is just okay, we can say is okay, a form of electrical energy. Right? Okay. What happens when okay, this electrical energy is okay, hits the bulb, it is converted into light energy. Right, okay. We can mainly as okay thank the inventor of the electrical bulb for that. Who was actually as okay, who said, well, okay, energy can change its form. Let me see if I can change electricity into light. And here we have it. Now, another thing that's going to happen is, okay, if I have, let's say, it's okay, 100 bulbs on like this. Probably not. But what's going to happen? Sooner or later, yes, okay, this room is going to be, yes, okay, unbearably hot. Because, okay, some of the light energy that this bulb here emits is then also going to be converted into heat energy. Or listen, even yes, okay, if you said, okay, yes, I want to change this bulb. Okay, you will switch off the light, but then you touch the bulb and it's you burn your fingers. Why? Mainly because, okay, some of the light energy that it produced was converted into heat energy. Okay, so yes, okay, this conversion of energy, yes, okay, is mainly, yes, okay, just taken to different levels. That's why we say, yes, okay, now sun, or what you call solar. Okay, because the sun has been around for, yes, okay, I'm not going to go into, yes, okay, the number of years. But now we actually say, well, okay, it provides heat or warmth, it provides light. But can we change this energy into other forms? Like electrical energy? Yes. Yeah, okay. So it's something that you see, yes, okay, on a daily basis. Your stove. Now I don't know whether you have gas in your house or you have an electric stove. Either form, yes, okay, gas that is going to be, yes, okay, a form of combustion energy. Okay, where you mean, yes, okay, just burn the gas and, okay, yes, it produces heat energy on which you are able to, yes, okay, you can say, okay, cook your food, boil an egg, make your dinner, lunch, whatsoever. Or if it was an electrical stove, yes, okay, it's going to produce heat energy. That electrical energy is going to remain, yes, okay, converted into heat energy, and you will be able to, yes, it's okay, cook your food or meal on that. Okay. So here, yes, okay, just because your tissue absorbs some of that sound energy, that sound energy is going to be converted into heat energy. And you can then mainly say, okay, the more heat energy a tissue absorbs, the more sound energy a tissue absorbs, more heat energy will be produced. Because that's means, yes, okay, just convert from sound into heat. And the more heat energy we produce, that's okay, the more likely is it that that tissue will be suffering from, okay, will develop what we call biological effects. Or we can say, okay, the effect that the sound has upon the tissue. Okay, so absorption is mainly as, okay, we can say is, okay, a two-edged sword. It's an acoustic propagation, it's due to acoustic propagation property determined by the nature of the tissue. That would say, okay, now this tissue is going to just, okay, absorb a lot of sound energy. And on the other side, that's okay, also going to be leading to your bioeffects or biologic effects. Now, two things, girls. And we can mainly say, so is there anybody who is in doubt what a okay absorption of energy was?
Me a little bit. Um,
Yes, Shaq, you said anything there?
Yes, I said just me a little bit. I get that it's a caustic propagation and it can be the biological effect. I just don't understand like so absorption is when the sound wave is absorbed into the tissue and
That's
it can,
pretty much it. Yeah,
okay,
clear?
yes.
Okay. But then we can say, yes, okay, it will, yes, okay, this absorption will also, yes, okay, lead to biologic effects. Because, okay, this absorbed energy here is going to be converted into heat energy, right? Clear? And what that heat energy is going to, is okay, lead to, if we can say it's okay, it's going to, is okay, be warming up or it's okay, heating up of the tissues. Okay. Which is all going to, yes, okay, it's just going to be a matter of, okay, how much warming or heating up of the tissue is it that the tissue will be able to, you can say, it's okay, withstand without suffering. That will determine as, okay, will it create bio effect or biologic effects. Did that make sense?
Yes.
Okay. So 2 things goes. First of all, is okay, we can say it's okay, absorption. That is also as okay going to be as okay directly proportional to the frequency. Or we can mean it's okay, just write it the other way around. Okay, where you mainly can say is okay, due to that, the high frequency sound wave will lead to as okay, more absorption. Whereas you can say it's okay, low frequency sound wave may lead to as okay, lesser absorption. Now let's just say that okay, as here is okay, it is the same tissue. Let's just say it's okay that the tissue here we have is muscle. Now, if this muscle here is okay, is going to be, let's say it's okay, scanned by a high frequency transducer. What we actually will have is that okay, there will be more absorption of sound energy. Clear? And due to as okay, there's greater absorption due to the higher frequency. That will mean cause that there's going to, we can say, okay, there will be as okay, a greater difference between as okay, the amount of energy in one versus 2. Mainly because a greater amount was absorbed as it passed through the tissue. Why? Because of a high frequency transducer. We can say, okay, we can say the high frequency that was, let's say it's okay, 10 megahertz. Whereas on the other hand, we can say, okay, this was the same muscle, which we is okay, scan with, let's say it's okay, low frequency transducer. We can say it's okay, less than 2 megahertz. Okay. Now the amount of energy in this sound wave here is okay, is the same as it was up here. What we can mean is as okay, due to as okay, the lower frequency. And it being as okay, the same tissue, what we mean is okay, we have in this case is okay, that's going to be as okay, a lesser absorption of sound energy. in this tissue. Okay, there is going to be some, but it's going to be lesser compared to what we had up here. Maybe meaning it says okay. Okay, but it's okay. This is still going to just okay be a lesser energy level and compared to just okay what we had here. But we can say, okay, here there's going to be as okay a lesser difference in the level of the energies because okay of lesser attenuation or lesser absorption, which contributes to as okay a lesser attenuation. There, okay, it was mainly as okay, just going to be the difference in the frequencies that determine that. Did that make sense? So frequency is directly proportional to absorption. So we can make it okay based on that said, or say just as we said for scattering, and not being for absorption, contributing to yes, okay, attenuation. Then frequency would not have been a factor of attenuation. Okay. Or mainly as okay, because of absorption, it's okay being a process, which is just okay, directly proportional to frequency. Frequency is okay, is a factor contributing to attenuation. Now goes out of all the tissues in the body. We can mainly say, okay, that max absorption is going to be as okay in the bone. So bone is going to be as okay a tissue where we can say as okay a lot of as okay the attenuation that happens to the sound wave traveling through the bone is going to just okay be due to absorption. Did you girls get that?
Yes.
Right, okay. We can also say goes that okay, as bone as a tissue is also going to be as okay a tissue that's going to cause a max amount of reflection. Or we can say out of all the tissues in the body, bone is going to be the one that's going to produce the strongest reflection. Did you ladies get that? Any questions? So these were the three main processes that contributed to attenuation. One is a reflection, the amount of energy that returns back. The other one was scattering, where it's okay, when sound wave hits a tissue boundary edge, disperses. And the third is absorption, because okay, that sound wave travels through the tissue. Some of the energy that it carried is going to okay be absorbed by the tissue. Clear? Okay. As far as reflection is concerned, we can say it's okay, the amount of energy that is going to okay get reflected back from different tissues is going to okay be determined by the nature of the tissue. Clear? So why? So like it's scattering. Okay, but we can say it's okay, scattering is going to be as okay directly proportional to frequency. Clear? Third was absorption, where we said absorption is okay, the amount of energy that's going to be as okay absorbed by a tissue is going to be determined by the tissue itself, where bone is a tissue with max absorption, in which max is okay, the greatest amount of absorption will happen. Okay, okay, but that is also as okay, it's, or we can say, okay, absorption is also going to be as okay directly proportional to the frequency. So same tissue is being scanned by as okay 2 different frequency transducers. You will have more absorption of sound produced by the transducer with a higher frequency, contra to the lower frequency transducer. Is that clear? Okay, so just remember, reflection, scattering, and absorption. These were processes, whereas path length and frequency were factors. Right? And what was attenuation? Decrease in the bigness parameters. You can simplify that. Then you can say, as okay, now what was the bigness parameters? That was your power, intensity, and amplitude. Okay. Which mainly is okay, is all about as okay, how much energy is it that, okay, how much energy is it that the sound wave carries? So that is going to as okay decrease as the sound wave propagates through tissues. Because every tissue it hits, some energy is going to be as okay get reflected. Some energy is going to as okay be scattered. And okay, some energy is okay may be absorbed as it passes through the tissue. Did you girls get that? And as a result of these 3 processes, the amount of energy that continues on is going to be lesser than what it was before that sound wave hit the tissue. And that's going to just happen again and again and again and again. So that's why we say, okay, the greater distance that's okay a sound wave travels, the more is it that it will attenuate. Where you may say, well, okay, what did we call that distance? We just refer it to as the path length. Where we say, okay, path length was directly proportional to attenuation. The greater the distance or the greater the depth that sound wave has traveled, the lesser and lesser and lesser energy is it that it will be carrying. Or we can say the difference of the initial energy to just, okay, that amount of energy at the very deep level is going to be greater because of a greater amount of attenuation. Did you ladies get that? Anybody who is in doubt?
No.
Now, please, girls, keep in mind that your frequency doesn't change. Okay. Okay. It just determines the amount of attenuation, which will be associated decrease in your bigness parameters. But the frequency will remain the same. Okay. If your transducer produces, that's okay. You can say it's okay, a frequency of 5 megahertz. That frequency will remain 5 megahertz even at a depth of 3 centimeters, even at a depth of 5 centimeters, even at a depth of 8 centimeters. That frequency will not change. Clear? So frequency remains the same. Capiche? But what it may cause is, okay, as we just said, more or less amount of absorption in a tissue, more or less amount of scattering at a tissue boundary. Because frequency was directly proportional to these two processes here that contributes to attenuation. So that was, yes, okay, we can say it's okay, your attenuation 101. Now, girls, please, yes, okay, take a few minutes or a few moments to, yes, okay, read on, yes, okay, these couple of pages here regarding, yes, okay, attenuation. And when we get back in, should we say 15 minutes? When we get back in 15 minutes, we will talk about, as okay, what we call attenuation coefficient. Okay. Is that clear? So see you ladies at 10:16. Okay, ladies. Welcome back. Now, does anybody have any questions about attenuation?
Can I just confirm a question I had?
Go ahead, my dear.
So for Rayleigh scattering,
Yes.
would you say frequency and Rayleigh scattering are directly related, right?
Yes.
Okay, thank you.
But here the difference is there's going to be as okay, the quadrant root of okay, as Rayleigh scattering is going to be the frequency. No, sorry, sorry. The quadrant root of frequency is going to be as okay, your Rayleigh scattering. But the simple thing is that okay, as the greater the frequency, the more it's okay, Rayleigh scattering.
Okay, I just wanted to be sure. I wasn't sure if directly meant like they both go up at the same amount. I know they're both increasing, but I didn't know if, okay.
No, it's going to be as okay, the quadrant root of okay, yes, the frequency is going to be as okay, the times that Rayleigh scattering will increase as well.
Okay, gotcha. Thank you.
Or if you go into decrease, it's the same. Okay. So they are both, yes, okay, directly proportional, but not simply directly proportional as scattering and frequency. Okay. So the formula is going to be the radius scattering is going to be okay directly proportional to frequency raised to the power 4. But that raised to the power 4 doesn't mean that you multiply the frequency 4 times or by 4, but you multiply its value 4 times. Just like a square becomes multiply itself twice. Cube 3 times. Did that make sense?
Yes, thank you.
Okay, no problem. Okay, girls. Now, what we mainly can say that's okay, or generally speaking, if we is okay, say attenuation. Clear? Now, attenuation mainly as okay, was just going to be as okay when we say yes, okay. If these are all different tissues, where we as okay may compare the intensity or power of this wave here. To as okay, we can say it's okay, the intensity or power of the wave over here. Clear? Okay. Now, since that's okay, there are yes, okay, a lot of factors that okay, yes, contribute to attenuation. And we can say it's okay, a lot of processes are involved in attenuation, which is going to just okay be different from tissue to tissue to tissue to tissue to tissue to tissue to tissue. Okay, that's why it's okay. It's going to just okay be as okay. Extremely difficult to just okay specify as okay how much attenuation is it that actually is okay occur at each tissue level. So mainly as okay, we can say it's okay to simplify as okay the overall discussion of attenuation. That's why as okay, we may actually as okay talk about attenuation in two forms, in two ways. One is going to as okay, what we will call as okay attenuation coefficient. There's another way of yes, okay, looking at attenuation. Or we can say, okay, sort of quantify the amount of attenuation that, okay, as sound waves may undergo. Is going to be as okay, what we later on today will talk as is going to be as okay, half value layer thickness. But both these, yes, okay, yes, okay, we can say it's okay. Entities here are mainly as okay, going to be as okay, two different ways of, we can say it's okay, quantifying attenuation. And may say, okay, how much attenuation is it that there occur? But just looking at, okay, as the attenuation in different ways. Is that clear? So first of all, it's going to be it's okay. We can say it's okay attenuation coefficient. And mainly as okay, just as okay, make it simple. We can say it's okay. Vernal blue is your attenuation coefficient. Now I may it's okay. Just want to say it's okay. When we say attenuation, what does that mean? By now, it's okay. You guys should be able to it's okay say does that mean it's okay means the decrease in the power, intensity, and or yes, okay, amplitude. Clear? That was what we call attenuation. That's okay. In this instance, it says, okay, the word coefficient is going to apply as okay to yes, okay, or we can say it's okay as the yes, okay, we can say this sound travels at depth of 1 centimeter. Did that make sense? So you can mainly say, okay, you can, where otherwise it says, okay, the amount of attenuation that a sound wave undergoes after traveling as okay a distance of 1 centimeter is going to be called an attenuation coefficient. Okay, now let's just take an image here. Now, what I said earlier in a previous chapter, yes, from point to point to point to point, here's okay, you mean said that okay, as there was a difference or there was a depth of 1 centimeter. Clear? So we can say, okay, this one here is the 1st centimeter, 2nd centimeter, 3rd centimeter, 4th centimeter, 5th centimeter, and okay, yes, the 6th centimeter. Now, when we say as okay, attenuation coefficient, what would that mean to me? That would mean it's okay, just mean how much attenuation is it that the sound wave underwent while traveling as okay, this depth here of 1 centimeter. You can actually even yes, okay, we from 0 to the 1st. So yes, okay, we say yes, okay. If this, for instance, okay, here was our transducer, and we say yes, okay, up here. Let's use this calculator. This was the intensity of the sentence, okay, sound wave. Or you can say, okay, this was just okay, the 1st centimeter that it traveled. So yes, okay, it is. We can make it okay, there is going to be as okay a difference between yes, okay, the power of the sound wave, power intensity and amplitude of the sound wave as it immediately leaves the transducer, and just okay at a depth of 1 centimeter. That difference between yes, okay, the power intensity and amplitude at this depth, where you can say okay, for me is okay, what I mean is okay, 0 centimeters. Versus this depth here, which is 1 centimeter. That difference in the power intensity and amplitude mainly going to say how much attenuation did this sound wave is okay. How much did the sound wave attenuate as it traveled to a depth of 1 centimeter? The amount of attenuation is okay, but this centimeter here is going to be as okay your attenuation coefficient. The same way as okay applies to this one here. Here it says okay, where it travels from a depth of 1 centimeter to a depth of 2 centimeters. It traveled another centimeter, right? Right. Okay, where we can mainly say okay, now the attenuation coefficient then would then be that okay, as how much did the sound wave attenuate while traveling from that depth of 1 centimeter to let's say it's okay a depth of 2 centimeters. Because the distance here is 1 centimeter. Clear? And the decrease in the power, intensity, and amplitude which is mainly going to be as okay compared. What was the power up here compared to as okay, where is the power down here? Is mainly as okay going to determine how much it attenuated. So that difference in the power, amplitude, and intensity, which is going to be as okay, greater at a shallower depth, lesser at a deeper depth because it traveled deeper. That is going to be okay, as a whole be as okay, what we call the attenuation coefficient. Okay. Now, anybody is in doubt about that? So what is the attenuation coefficient? Mainly as okay, just how much does a sound wave attenuate after it has traveled, yes, okay, a distance of 1 centimeter. That will be, yes, okay, your attenuation coefficient. Did that make any sense? Now goes the unit for this value here. Your unit for the attenuation coefficient is mainly as okay going to be as okay, where we can say as okay. Now what was going to be the unit of attenuation? Okay, the unit for attenuation was decibels. Clear? Okay. And okay, as since yes, okay, we here says okay, this coefficient mainly as okay was just accounting for as okay a depth of 1 centimeter. So that's why it's going to be as okay decibels per centimeter. Did you guys get that? Okay. Did you girls get that?
Yes.
Good. Now, if you look at this definition here, we can mainly say as okay. Now that can be as okay. We may have okay as a greater degree of attenuation. Or we may have okay as lesser attenuation per centimeter, right? Okay. Maybe in this case, I can say okay that okay as far as attenuation coefficient is concerned. The pattern is, we can say it's okay fixed, or we can say it's okay will be constant at 1 centimeter. Okay. Because maybe that's okay, it just says okay as the sound traveled 1 centimeter, how much did it attenuate? That amount of attenuation per centimeter is going to be as okay, we call this okay attenuation coefficient. Then this whole thing here is okay as per because it means okay, just talk about it's okay. per centimeter. That is okay as a fixed path length to which, yes, okay, we compare the amount of attenuation that the sound wave undergoes. So mainly because, okay, this here is fixed as, okay, as 1 centimeter. Okay, we can't really say that, okay, as that the path length of your attenuation coefficient is going to be, it's okay, directly proportional or inversely proportional to the overall attenuation. Where we can mainly say, okay, the greater, yes, okay, your attenuation coefficient, mainly, yes, okay, will be leading to, yes, okay, a greater attenuation. Whereas, okay, as a lower attenuation coefficient. Mainly, as okay, will lead to a lower overall attenuation. Which mainly is okay, just would mean that, okay, yes, your attenuation coefficient is going to be, as okay, directly proportional to attenuation. Or because, okay, mean as okay, just say as okay, that will be as okay, your total attenuation. So where you want to say, let's not say this. Where we then say as okay, this general attenuation here, that was just okay. That was directly proportional to frequency. Right? Okay. Which then also, yes, okay, make your attenuation coefficient, yes, okay, directly proportional to frequency. We can't really say that, okay, yes, we cannot say that, okay, yes, attenuation coefficient is directly proportional to path length. Because, like what we said, as far as, okay, as your attenuation coefficient, that the path length was fixed at 1 centimeter. Because your attenuation coefficient mainly is okay, just talks about how much does a sound attenuate as it traveled at depth of 1 centimeter. Clear? But if you say, yes, okay, if a sound wave, yes, okay, have a greater attenuation coefficient, that will mean, yes, okay, mean that it attenuates by a great number of decibels, or attenuate to a great extent by traveling 1 centimeter. That mainly will mean that, okay, the overall attenuation of this sound wave as it travels deeper and deeper and deeper will be greater. Clear? Where we can mean says, okay, the common factor that will cause both of these two here is okay, increase was going to be the frequency. or decrease. Did you girls get that? Did you girls get that?
Yeah.
Yesterday I sent 2 of you girls on shopping, right? When we talked attenuation, right? I said, well, okay, yes, just assume that, okay, yes, different frequencies. Let's just say that, okay, the distance between shop to shop to shop to shop here was just, okay, 1 centimeter. Now the girl who, yes, okay, was a frequency or was a sound wave that came out of a high frequency transducer. Well, let's just write all this down. So we have a black and white. Or colorful and white. We can mainly say that's okay. Here and here. Let's just say that these are 2 different transducers. We can say it's okay, this may be as okay. A high frequency transducer. Let's say that okay, as it's going to be as okay, a frequency of 10 megahertz. Whereas this fellow here is okay, is a low frequency transducer. Let's just say it's okay, okay, yes, 2 megahertz frequency. Now what we already know is that okay, yes, this transducer is okay, mainly is okay because of its main high frequency is going to is okay have a great attenuation. Yes, okay, the frequency is still going to yes, okay, be directly proportional to the lower frequency, but it's okay. So it's okay, it's still directly proportional to low frequency or to the frequency attenuation, sorry. That the frequency of this transducer is still going to yes, okay, be directly proportional to attenuation, but because of a low frequency is okay, this will be as okay, lesser attenuation. Okay, now we can mainly say as okay, here, 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 here. And let's just okay, assume that okay, as the distance between this to this is 1 centimeter. Likewise, okay, the distance from this to this here is also 1 centimeter. So why here? This is a distance of 1 centimeter. This is a distance of 1 centimeter. Clear? So ladies, yes, okay. Both of these transducers here is okay, they produce sound wave with the same power intensity. Let's say that okay, here the intensity is okay, the intensity of both of these here power was, let's say 100 watts. Now, mainly because, okay, this was a high frequency transducer. There's going to be, okay, a greater degree of attenuation between, let's say, this point here and this point here. So we can say, okay, it may attenuate to, let's say, okay, 1. Which is, okay, 100. Where we mean is okay, we just have okay as an a power of 1 watts. Where here is okay, meaning it's okay due to this being a low frequency transducer. That would be as okay a lesser attenuation. So it's okay, it may just reduce to it's okay 1/10. Or it's okay, reduce attenuate by 1/10, whereas here is going to it's okay, attenuate to 100. So it's okay, here we actually it's okay, we'll have okay as a power of 10 watts. Clear? So when we compare as okay 10, 100 to 1 watt, we can mean is okay, this was going to be as okay a great attenuation coefficient. Because attenuated to as okay 1/100 of the initial at a depth of 1 centimeter. Where here it's okay, since we have a lower attenuation, we have a lower frequency transducer, there's going to be as okay a lesser attenuation, and that's why it's okay, it only attenuates to 1/10 of the initial, which was initial was 100 watts, but it's going to just okay, just attenuate to 1/10 of that, which is going to mean that we still over here is okay, have an intensity of 10 watts. So in this case, it's okay, underwent lesser attenuation per centimeter. Okay. Did that make sense?
For me, for the 2 megahertz one, I don't get how you got 1/10.
It attenuated to just 1/10. What is 1/10 of 100?
10.
Okay. So that's what you have here. You have $100 at the beginning of the day. At the end of the day, you have only 1/10 left. How many dollars will you have?
10.
10. On the other hand, yes, okay, you had $100 at the beginning of the day. At the end of the day, you are left with 1/100. So how many dollars will you have?
1.
1. What did that mean? That means you started your day with $100 and ended up with $10. Well, okay, yes. The decrease on the amount of money that you had in your wallet, pocket, purse, whatever the hell you call it, is less. Compared to, yes, okay, when you compare that $100 versus $1, right?
I was just confused because I'm like, where did we get the 1/10? I understood the 1/100.
Okay. So 1/10 is made it as okay as that it attenuated to 1/10 of the initial. Okay. That's why I says okay, all comes down to yes, okay. When we talk of attenuation or anything that's going to be as okay expressed with the unit decibels. It's mainly just, and that's why they say it's okay, it is a relative unit. Relative related to yes, okay, mean is okay, comparing to yes, okay, what did you start with to what did you end with? Did that make sense?
Yes, so basically they start with the 100 and then
exactly. In both cases, we just kept that constant just to avoid too much confusion.
Okay.
Clear? Okay.
Okay.
But in one case, that's okay. We said that okay, yes, or it's okay, or 100 volts after traveling, yes, okay, this fixed depth of 1 centimeter, it attenuated down to 1/100 of the initial. So we are left with 1 volt. Where we can mean says, okay, because me is okay, this is a greater attenuation compared to as okay, that it only attenuates to 1/10. Okay. There, okay, as in this case, that's okay. On both instances, that's okay here. The distance is the same. So attenuation coefficient here is made as okay, that's going to as okay, that it attenuated to 1/10. In this example here, versus here, it's okay, attenuated to 100. Which mainly mean that okay, yes, here, yes, okay, or we can okay, just label this one here as transducer A and transducer B. In transducer A, we have a greater attenuation coefficient. Right, okay, compared to in B as okay, where we have okay as a lower attenuation coefficient. Because it attenuates less per centimeter compared to as okay, transducer A where it attenuates more per centimeter. Where okay, as in your attenuation coefficient, the path length is fixed, is constant. In both instances, he says, okay, how much did this 100 watt attenuate per after a centimeter? How much did the sound radius okay attenuate after traveling a depth of 1 centimeter? Here it attenuates to 100 of the initial, which was 100 volts. So yes, okay, we are left with just 1 volt. Which is going to be as okay. Because it generally as okay is because of okay, it's a greater attenuation. There here it's okay, that's going to be as okay, a lesser attenuation. So we start with 100 watts, but due to as okay, a lesser amount of attenuation per centimeter, it is going to be as okay, just attenuating by attenuate to 1/10 of 100, which is going to be as okay, we are still left with 10 watts. Did that make sense? Where we can mainly says, okay, now why do we have yes, okay, greater attenuation coefficient here? Mainly because this transducer here is okay, was a high frequency transducer. Whereas, okay, in example B, yes, okay, we have a lesser attenuation coefficient, which is just going to be, okay, how much did the sound attenuate after traveling as, okay, this fixed depth of 1 centimeter is going to be low. Why? Mainly because this one here was a low frequency transducer. So what does this here establish? Or what does this here establish? It establishes the main thing that we can say is, okay, that attenuation coefficient is going to be as okay, directly proportional to frequency. Yeah. Did that make sense? Did that make sense, girls? Did that make sense?
Yes.
Yes.
You are this close from me closing the session. Okay. So higher frequency, more attenuation coefficient. Lower frequency, lower attenuation coefficient. Now, what we mainly as okay will say for this case here, or for A, that okay, yes, the attenuation coefficient, that's going to be constant. So for B, is constant. What would that mean? That for each centimeter that the sound wave travels, well, this was for the first centimeter, for the next centimeter, it's still going to just okay reduce to just okay 100. This here is okay, still just going to just okay reduce to 1/10. So what would that mean? That would mainly mean that okay, as after traveling at depth of 2 centimeters. Or okay, for the first centimeter, that's okay, in transducer A, that's okay, the intensity went, or the voltage or power, sorry, went from 100 watts to 1 watts because it reduced to 100. Clear? Now that's okay, what we have traveling from here is just going to be 1 watt, and that's again going to reduce to 100. So that mainly means that okay, it's over here. We will have okay as an even lower volt of power, which is going to be okay 0.01 watt. Yes, okay, over here, what do you have? This was 10 watts, but it's just going to reduce to 1/10 because the attenuation coefficient is going to remain constant. So here is okay, our power will actually, that's okay, at this level here will become 1 watt. Let's just say that okay, as it travels, that's okay, another centimeter. And another centimeter. This is, that's okay, this power means that's okay, this proceeds from here to here for another centimeter. That's okay, here was 0.1 or 0.01 watt. It's going to, that's okay, decrease to another, that's okay, 100 part. Where over here is okay, meaning it's okay, that's become it's okay, 0.0001 watt. Whereas this 1 watt here is still just okay, just going to just okay, attenuate by the same as okay, 1/10. So at this point, it's okay, here that will become yes, okay, just 0.01 watt. So girls, just keep in mind that okay, as whatever your attenuation coefficient is going to be determined as okay, that's going to remain constant. That's going to remain constant per centimeter that the sound wave travels. Did that make sense?
Yes.
Okay, so if you said yesterday, yes, okay, I said, yes, okay, we had 2 girls. Right, okay. Here we can say, yes, okay. There's high frequency, that means it's going to mean that, okay, as she will spend more money per shop. Clear? And here we can say, as okay, there's low frequency, yes, okay, that means, yes, okay, will just mean that this girl here is okay, a person is okay, he or she will, yes, okay, spend. We can say it's okay, less money per shop. Now let's just assume that, okay, I hear the distance between is okay, a shop to shop to shop is 1 centimeter. Now you both, yes, okay, yes, okay, you both started with, you can say it's okay, $5,000. Now here is okay because we have a thrifty spender in A versus B. She may say, well, okay, you know what, I'm going to spend $2,500 per shop. Whereas down here we will say it's okay, we just spent, it's okay, $250 per shop. What will happen here? Yes, okay, her $5,000 is going to be, yes, okay, finished after, yes, okay, visiting 2 shops. Right? Where you say, it's okay, she is okay, attenuated from, yes, okay, 5,000 to 0 after 2 centimeters. Or is okay after, yes, okay, traveling to or visiting 2 shops, because in each shop, yes, okay, she spent 2,500. But 2,500 here, 2,500 here. That's okay. $5,000 gone. Where okay, as the lady who only spent $250 per shop will be able to just okay carry on for a greater distance before as okay this 2,500 or $5,000 are spent. As a matter of fact, yes, okay, she will be able to just okay shop in 20 shops before all her money is gone. Did that make sense? But it's okay, whoever A was, she said, well, okay, whichever shop I'm walking into, yes, okay, I'll be spending $2,500 per shop. Whereas B is okay, I had chosen wisely and said, well, okay, my main, and that's okay, my budget per shop that we walk into is going to be $250. And that's the fixed. That's fixed. So is this fixed. So that's what we mainly say is okay, attenuation coefficient. It's me is okay, just saying it's okay. How can we quantify it? Okay, say, well, okay, a sound wave will attenuate this much per centimeter. Did you girls get that? I say as okay, as far as the path length is concerned, or your attenuation coefficient, yes, okay, that is constant, that is 1 centimeter. So it just says, okay, how much does the sound attenuate after traveling as okay at depth of 1 centimeter? That well, okay, that value is going to be constant. Clear? And it is going to be directly proportional to the frequency. Did you ladies get that? So higher frequency transducer will have a greater attenuation coefficient, which may mean that, okay, as per centimeter, it will attenuate more, which may mean that, okay, as that sound waves, okay, will attenuate at a shallower depth. That makes sense. Whereas, okay, if we went for a low frequency transducer, we say, well, okay, low frequency, lesser attenuation coefficients or less attenuation per centimeter. Clear? Which may now mean that, okay, that sound wave, that's a constant amount, so that's okay. It will be able to travel to a greater depth before attenuating. Completely, right? Did you girls get that?
Yes.
Good. Okay. But the attenuation coefficient, if it's well, okay, yes, it is 2 decibels per centimeter. That means that, okay, for each centimeter that sound travel is going to, okay, attenuate by 2 decibels. If it's at 3 centimeters per decibel, oh, sorry, 3 decibels per centimeter, that's going to be, okay, that value will remain fixed or constant. Did that make sense? Okay. So for you, yes, okay, what we actually, yes, okay, then we'll say, yes, okay, will be, yes, okay, total attenuation. Okay. We can say, it's okay, your total attenuation. Now this equation here is okay, that's going to be important. It says, okay, just make sure that, okay, yes, you remember it. Because how we will do always that we, yes, okay, will determine the total attenuation that, okay, as a sound will undergo. That's made as okay, that's going to be as okay, we can say it's okay, the product of yes, okay, or attenuation coefficient. Multiplied by the path length. Where we know in this case, I can say it's okay. The greater the attenuation coefficient, and or yes, okay, the greater the path length. The greater is going to be yes, okay, your total attenuation. Clear? Yes, okay, as we go vice versa and say yes, okay, shorter the path length and or lesser attenuation coefficient. lesser will be as okay your total attenuation. Now we can just take an example and say as okay, if we, for instance, okay, have an attenuation coefficient which is going to be as okay 2 decibels per centimeter. And just remember, guys, that this is going to be constant. Because we made as okay, so this is that's okay as a simplified way of saying it's okay. Approximately as okay, how much does the sound wave attenuate after traveling as okay a distance of a centimeter? But then the question comes as okay, how much will it attenuate at a depth of whatever distance? We can here say it's okay that we keep the distance, let's say it's okay 5 centimeters. Clear? Now in this case, yes, okay, our total attenuation mean is just going to be as okay 10 decibels. Okay. Why? Because 2 times 10 or 2 times 5 is 10. That's what it is. Now some of you will say, okay, then why only decibels? Well, first of all, yes, okay, the unit for yes, okay, total attenuation or attenuation alone is just decibels. But even yes, okay, if you look at it, you can say it's okay, it's just going to be decibels per centimeter multiplied by centimeter, which mainly as okay will just mean the same as we said, decibels per centimeter multiplied by centimeter. So practically or mathematically, it's okay, these two cancel out one another, and that's what we're left with. Which becomes just okay, the total attenuation at a depth of 5 centimeters if our attenuation coefficient was 2 decibels per centimeter. Yeah. Did you girls get that? So please do not say that, okay, the unit of total attenuation is also going to be decibels per centimeter. Okay, the unit for total attenuation is means okay, just what was the attenuation after yes, okay, traveling a distance of 5 centimeters in this case here. We can say it's okay, we keep yes, okay, the same as okay attenuation coefficient. Just for this next example here. He says, okay, we still says, okay, our attenuation coefficient was 2 centimeters. But let's just say, okay, increase the path length to yes, okay, a total of 10 centimeters. So we can mainly say, okay, because okay, we went from 5 centimeters to a total path length of 10 centimeters. What we actually will see is that, okay, as our total attenuation is going to be as okay, 2 times 10 becomes 20 decibels. So the reason is okay, in this instance here is okay, that our attenuation, our total attenuation is okay, increased. Although it's okay, we kept the attenuation coefficient at 2 decibels per centimeter, while that we increased the depth of the image from 5 to 10 centimeters. Did you guys get that? That we can then say is okay, this total attenuation here is low mainly because okay, we have a low path length. Although it's okay, the sound is okay, attenuated at the same amount per centimeter. Did you guys get that?
Yes.
Okay. Likewise, we can just okay, just say as okay. Now for this next example here is okay. On this set of examples is okay. We may as okay, we just keep as okay our path length the same. But if we say that okay, as in one example, yes, okay, we may have, let's say as okay, small attenuation coefficient, 3 decibels per centimeter. What do I mean? That per 3 centimeters or per centimeter that the sound wave, yes, okay, travel, it reduces or attenuates by 3 decibels. Our question is, okay, how much will it just be the total attenuation if it travels for a distance of 5 centimeters? So per centimeter, 3 decibels multiplied by 5, which is the total depth, is going to mean that, okay, in this case, it will have, okay, as a total attenuation of 15 decibels. Right, okay, but we can mainly says, okay, but just because we kept this, okay, we can say, okay, this is the lower attenuation coefficient compared to, okay, what we have, yes, okay, our total attenuation will be lower. Although it's okay, we kept the, or in this instance, we keep the attenuation, we can say it's okay, the path length the same. Whereas, okay, as if we now just okay, just we can say it's okay, increase the attenuation coefficient. Let's say it's okay that we go to as okay, let's just double this and say, well, okay, it's not just 3 decibels per centimeter, it actually attenuates by 6 decibels per centimeter. Now you multiply these two numbers and what do you see? That okay, as our total is going to be as okay, be 30 decibels. Did that make sense? And we mainly can say, okay, your total attenuation. As we mainly as okay said when we started attenuation to begin with, or directly proportional to yes, okay, to both frequency. And it was also as okay, directly proportional to the path length. Clear? Whereas, okay, we can say, okay, what is going to be as okay, the relationship between the total attenuation and yes, okay, the attenuation coefficient. Your total attenuation and attenuation coefficient is also going to be directly proportional. which mainly is okay is because it's okay, both of these two here is okay are directly proportional to the frequency. So higher the frequency, higher your attenuation coefficient. Lower the frequency, lower the attenuation coefficient. Higher the attenuation coefficient, higher your total attenuation. Lower your attenuation coefficient, lower the total attenuation. Did you girls get that? But the equation of okay as of how to calculate is okay the total attenuation that sound undergoes. But that is okay, whatever value is being given as your attenuation coefficient, that remains constant. Clear? Okay, and what is that attenuation going to just okay be related to? The frequency of the transducer. Because when we talk attenuation coefficient, it's okay, your path length is fixed. It's not going to be per 2 centimeters. It's not going to be per 3 centimeters. It's per centimeter that the sound wave travels. Did you girls get that? Now, if you look on your page 85, yes, okay, the first equation that is given is okay as your total attenuation, right? What we just did. Okay, your total attenuation is going to be equal to the product of attenuation coefficient, which was attenuation per centimeter, multiplied by the distance. Here, distance means yes, okay, is going to yes, okay, be relating to yes, okay, the path length. Or we can say, yes, okay, the total distance that the sound traveled. Did you girls get that? So if you are given yes, okay, a question where it asks, okay, as a sound attenuates 4 decibels per centimeter. It travels to a depth of 4 centimeters. What is your total attenuation? Four decibels per centimeter to a depth of 4 centimeters. What is your total attenuation?
8.
Huh?
8.
Why would it be 8?
16.
4 times 4 is
16.
16. It's going to be the product of it. Okay, Jen? It's the product of it. Mainly if I say that's okay, for each mile that you travel, you spend 20 calories. Well, okay, that's going to be a very low calorie mile, but that's just okay. You spend 20 calories per mile that you travel. How many calories would you spend if you as okay have traveled a distance of 5 miles? You would just say, okay, I spend 20 calories per mile. I travel a total distance of 5 miles. That's going to be as okay. The total calories will be. Yes. What is 20 times 5?
100.
Is your name Jennifer?
Oh, I didn't realize you were talking to me. Sorry.
Ah, okay.
I thought you were just asking another question.
Okay.
100.
You had to spend 100 calories, right? Okay, so that's going to be as okay, the total calories that you burn in after that's okay walking. let's say it's okay, 5 miles. Clear? Because that's okay, what made you, yes, okay, use less calories? Because, okay, you were only carrying, yes, okay, your own weight. Or we can, yes, okay, in terms of attenuation, say, yes, okay, here, this was a low frequency transducer that you came out of. We can actually, yes, okay, cause you to, yes, okay, use more calories as you travel a mile or walk a mile.
I think I misheard you on the first one because I thought you said 4 and 2, not 4 and 4.
Okay,
That's why
no, that's fine. Yep. Okay. So yes, okay, what will we make sure, what can we do to make sure that, okay, as you will burn more calories as you walk a mile? You may say, okay, well, Jennifer, yes, okay, you weigh this much, but here's some extra weight. We have this backpack filled with just, okay, rocks. Okay, now we have this backpack, and now, yes, okay, what's going to happen? For each mile that you will be walking, yes, okay, you will not be just burning, yes, okay, 20 calories, you will be burning 200 calories. So after that 5 miles, that's okay. We are not just looking at 100 calories as a total amount of energy that was burned, but that's okay, 1,000 calories. And we're going to be looking at a person who is sweating like hell. Did that make sense? Okay. But mainly it says, okay, so what is going to say, okay, in terms of the attenuation coefficient, and it's okay, overall attenuation, what is going to be as, okay, the common factor that increases both. The common factor that will increase both is going to be the higher the frequency. So attenuation coefficient and attenuation both were as, okay, directly proportional to frequency. Clear? So higher the frequency, higher is going to be the attenuation coefficient, and greater will be as, okay, the total attenuation of the sound traveling as, okay, a fixed distance. Where in your attenuation coefficient is, okay, the distance is fixed. So you can't just because you want to, yes, okay, say, well, like I want to explain, yes, okay, I want to define attenuation coefficient as the amount of attenuation per 3 centimeters or 5 centimeters. No, that distance is fixed. So you could say, okay, oh yes, okay, you guys is, okay, running a marathon, and it's going to be, yes, okay, how much energy will you be burning per mile? Yeah. Because it's okay, that will be, it's okay, your calorie coefficient. Did you girls get that? Okay. Now, ladies, if you look at the second equation, and again, yes, okay, please mark it, please highlight it, because that's going to be, as okay, an important equation as well. Okay. Because we mainly say as okay, now yes, okay, from this equation, as okay, one thing that we can mainly say is okay, or the term is okay. What we get out from this equation here is that, okay, yes, the attenuation coefficient. Now, mathematically, we mainly says, okay, just going to be equal to, yes, okay, your frequency. And please keep in mind here is okay that this frequency is okay is going to be as okay as well also expressed in megahertz. Yeah. And what is it that we do with this? That's okay. Frequency in megahertz. We divide that by 2. And that is going to just okay give us just okay the attenuation coefficient, which is going to just okay be expressed in decibels per centimeter. So we can maybe just okay just take 2 examples and say yes okay. The attenuation coefficient. What's going to be as okay the attenuation coefficient if you, for instance, okay, have a frequency or transducer of a frequency of, let's say, 10 megahertz. Now that 10 is mainly as okay, just simply going to just okay be divided by 2. And what that gives us? 10 divided by 2 mainly becomes 5. So that mainly as okay will mean that okay, as in this case as okay, the sound wave will attenuate by as okay 5 decibels per centimeter. We can just in this case as okay mean as okay when comparing this as okay, this was okay the high frequency transducer which means as okay just led to as okay a great attenuation coefficient. Whereas okay, as on the other hand, if we say okay, what will the attenuation coefficient be? If we had okay as a low frequency transducer. But still as okay is going to just okay be divided into half. But as okay, we can say as okay, we have a low frequency transducer. So let's say it's okay, just 4 megahertz. I mean, it would mean that okay, yes, in this instance, yes, okay, our attenuation coefficient is going to be nothing but 2 decibels per centimeter. But we can mainly say, okay, because of high frequency, we had a great attenuation coefficient. And okay, yes, because of low frequency transducer, we have a low attenuation coefficient. But mainly, yes, okay, we can actually just okay calculate the attenuation coefficient if we are given yes, okay, the frequency. So you may be given a question, or you can be asked simply, what is the attenuation coefficient of a 3 megahertz transducer? So that's going to be as okay 1.5 decibels per centimeter. How do we get that? You just divide that frequency in the megahertz by 2. And that will give you as okay the amount of, or you can say it's okay the value of the attenuation coefficient, which then remains constant. And then you can say it's okay. In both instances here, it's okay, we had this transducer and this transducer. Okay. And we can say it's okay. And they asked, okay, what is the total attenuation? What is okay as the total attenuation? We can say it's okay at a depth of 3 centimeters. Let me say sorry here. Okay, at a depth of 3 centimeters. And okay, yes, your total attenuation mean yes, okay, there's going to be yes, okay, when you multiply this by 3. And you multiply this by 3. So here you can say, okay, that total attenuation becomes 5 multiplied by 3 becomes 15 decibels. 2 multiplied by 6 becomes 6 decibels. Okay, but just okay, if you just are giving yes, okay, the frequency of a transducer. That number half is going to give you yes, okay, the numerical value, or it's going to yes, okay, calculate, maybe you to calculate the numerical value of your attenuation coefficient. Okay. Now that is the direct way of looking at it. Okay. You can even be asked something like, and let me just give you this, okay. So it's okay that the attenuation coefficient doubled equals your frequency. Although yes, okay, you still have to yes, okay, keep in mind, okay, this is still going to be expressed as okay as in decibels per centimeter, where okay, as the unit here is going to be as okay megahertz. Now, some of you may say, Mike, where in the hell did you get that one from? Just look here. If we say that, okay, yes, your attenuation coefficient was equal to, yes, okay, your frequency divided by 2. Then that will be the same as saying, yes, okay, because it's okay, frequency is equal to attenuation coef multiplied by 2. How did we get that? We multiply both sides by 2. We had this many and cut this, and okay, as now we are left with this. It just became okay, as we can say. So,
I have a question.
yeah,
So that times 2 for the attenuation coefficient, is it times itself twice, or is it actually times 2?
times 2, whatever your value here was. If it was 6, you multiply that by 2.
Okay.
Clear? And what do you get? You will get, okay, you say, okay, that frequency of that transducer was going to be as okay, 12 megahertz. So it's multiplied by 2. It is not squared. Clear?
Okay, thank you.
And why would it not be squared? Because, okay, we didn't write it as this. Had it said, okay, as the attenuation coefficient squared is equal to the frequency. Then, okay, I said we 6 times 6. You mean you said, okay, if that was the case, then okay, as 6 was mean squared. Then 6 squared would actually mean 6 times 6. Then you say, okay, that would be yes, okay, at 36 megahertz frequency transducer. So you can be asked in either way. You can be given a frequency and be asked to calculate the attenuation coefficient. That you just, okay, as divide the frequency in half. And whatever number you get is going to be the attenuation coefficient. Okay, and please here remember that, okay, as your attenuation coefficient is not going to be expressed in megahertz or kilohertz or gigahertz or tigahertz or whatever. The unit for your attenuation coefficient is decibels per centimeter. Likewise, that's okay, you can be given, yes, okay, the value of an attenuation coefficient and be asked to calculate the frequency of that transducer. Then you just double it. Don't square it, because the equation was of attenuation coefficient was frequency divided by 2. Clear? Yeah. It was not frequency squared divided by 2. That was not the equation. So multiply by 2 and raised to the power 2 is 2 completely different things. Yeah.
All right, so just to recap, so to get the frequency, you times the attenuation coefficient by 2 to get the frequency?
You just multiply the attenuation coefficient by 2 to
Okay.
get the frequency. I just gave you yes, okay. Listen, girls, I just gave you yes, okay, the simple yes, okay. Basic mathematical way by which you got it. By which from this equation here, which says, okay, as attenuation coefficient is equal to the frequency divided by 2. Now, girls, what does this is equal to mean? That may mean that, okay, as the numerical value on this side here is going to be equal to, as okay, the numerical value on this side, right? Clear? Now, if you want, just okay, do something like this and you say, well, okay, I still want to play around with this equation. So this number that we get here is still going to as okay equal to as okay what we have over here. Now, since here is okay, we divided frequency by 2 to get the attenuation coefficient. You mean yes, okay, just multiply both sides by 2. Now, frequency doubled, divided into half is your frequency. Which means, okay, then there's okay, it's going to be equal to twice the value of your attenuation coefficient. That we can say as okay, attenuation coefficient. If you find says okay, want to calculate that, we say as okay, what is that going to be if we have okay as a 8 megahertz transducer? It is going to be as okay what we can call 4 decibels per centimeter. Did that make sense? So we say here's okay, our value was of okay, that's what's going to be as okay 4 decibels per centimeter. But if we then on the other hand says, okay, what is going to be the frequency of a transducer if it had an attenuation coefficient of 4 decibels? Then you mean it's okay, just multiply that by 2. And what do you get? 4 times 2 becomes what? 8. I say as okay, we calculate as okay, the frequency that's going to as okay be expressed in megahertz. So that's when it says, okay, right hand side is equal to left hand side. Because what does the sign of equal means? That whatever is written on one side of the equal to sign is going to be equal to the worth of what is on the left hand side. So yes, okay, these 2 or 3 equations here, yes, okay, are important. Clear? So you can be given as okay, the frequency of a transducer and ask what is the attenuation coefficient. You can be given an attenuation coefficient and being asked, okay, as what is the total attenuation? Right. You can be given as okay, a total, or you can say okay, you can be given an attenuation coefficient and be asked as okay, what was the frequency? Okay. So for your attenuation coefficient, just remember goals, that value will remain constant. And it is directly proportional to the frequency. Any questions? Any questions, girls? Okay. Then I can guess, okay, just refer you girls to page number 86. Does everybody have their books? Is that book open up on page 86? Recall what we see on page 86. As you may, yes, okay, see a table that says 6.4. Do everybody see that table?
Yes.
Good. And what it mainly SOK just does, we SOK go from things such as water. We can say SOK other body fluids. We can say SOK fat. I'm just going to SOK change the color of this one here. Soft tissue. And then we go back to SOK things such as muscles. We go to SOK things such as bones and lungs. And then last is going to be SOK here. But we mainly see here again SOK that soft tissue is going to SOK what we can call SOK an intermediate attenuation. Yeah, we can say SOK water is lowest attenuation. We can say SOK this one here will be low or lower. And we can say okay, this one here will be low. Whereas we go beyond soft tissue, SOK is going to be high. Higher. And highest. So this is mainly SOK just a list of the tissues and the attenuation that occurs if you go in this direction here is going to be SOK attenuation in increasing order. Because we go from lowest to highest. Clear? Whereas if we went in this direction, that means SOK going to be listing SOK our attenuation in the different medias in a decreasing order. Why? Because it is going to be highest, lesser than bone and lungs, lesser than muscles, then okay, as the intermediate is going to be your soft tissues. Then yes, okay, lesser than soft tissue is going to be fat, lesser than that is going to be body fluids, and the least attenuating medium is going to be here. Is that clear? So goes this list. Whether you want to, yes, okay, remember it in increasing order, or whether you want to remember it in a decreasing order, that's wholly and solely up to you. Okay. Now it may as okay be looking pretty much same as that's okay, your propagation speed. Pretty much bias, okay, there's a little glitch here, mainly because that's okay. As far as speed was concerned, this one here was going to, yes, okay, be lowest, right? Whereas, okay, as far as attenuation is concerned, air is going to be the highest. And why? Mainly as okay, due to scattering. So for lungs. Because what is that we have in the lungs? That's okay, we have the alveoli. And what is it that the alveoli here? Here. Clear? Now, some of you says, okay, most of all is okay, body fluids. Bigger or lesser proportions of says, okay, your body fluids are made up of water. Or what I actually call is, okay, body fluids. Although it's okay, they may be made up of, you can say it's okay, water. You have, okay, as a slightly as okay, greater attenuation than plain water is mainly because, okay, in water fluids, and body fluids, sorry, we had waters, but it's okay, they are going to be as okay, different particles. Those particles may be cells. Those particles, that's okay, maybe we can say, okay, if we say plasma. If we took out all the cells, you still have proteins, exactly. You still have other things in it, different salts and so on. So then, okay, yes, when hit by a sound wave, that's okay. Probably not going to cause much of a reflection, but it's okay, a great degree of scattering. But as I said, okay, in all, that's okay, most lists that we have, that's okay, meaning it's okay, just two lists. One was the propagation speed. One was, okay, as your attenuation. The tissue that we have in the middle always going to be as okay, the intermediate. But that was okay as taken in context to speed, or as okay in context to attenuation is the soft tissue. Is that clear? Is that clear, girls? So two lists that may look alike if you don't look carefully, or you may get confused, or may just tempted to just okay, go and say, okay, but there's a difference. And I will mark that out, right? Okay, that in terms of speed, ear or lung had the lowest propagation speed, but it's going to just okay have the highest attenuation. That's the main difference between speed, the list of speed, and list of attenuation. Did you girls get that? Hey, Now goes. Just look at the last paragraph. On page 86. And what I want you girls to do is mark it. No, I will mean yes, okay, just okay, see. Let's look at it. Let's say this is a muscle. Similarly, this is also a muscle. Clear? We can say it's okay if we scan this muscle from here. And we scan this muscle from here. Okay. Now the difference in these two muscles here is that, okay, as we can say is okay. In this muscle here, that are underlined with blue, the fibers of the muscle are going to be running like this. Mainly because says, okay, this was an example of OPS, a longitudinal muscle. Compared to is okay. This say other muscle here is okay, where the muscle fibers were going to is okay, run like this. Which we mainly could say is okay, what's an example of okay, a circular muscle. Now, although yes, okay, goes both of these, yes, okay, could be yes, okay, the same type of muscle because both of these were as okay examples of okay as a skeletal muscle. So it's okay, their buildup. We can say okay, the type of muscle cells and so on, so that they were built up of was the same. But as okay, they will still have okay as because it's okay, the attenuation of this muscle here is not going to be equal to the attenuation of the other muscle. So the question then just arises, which of these two muscles here will it be as okay, the longitudinal muscle? Or is okay, the circular muscle? And please keep in mind here is okay, the arrangement of the fibers is related to is okay, we can say it's okay, the direction of the beam or related to the beam. Now, which of these two here is okay, will have the greater attenuation and which will have is okay, a lower attenuation.
I think the longitudinal is going to have a higher attenuation and the circular is going to have a low.
Mhm.
based on your drawing.
So you say that this one here is greater.
Yes.
This one here is lower. Okay. Anybody else?
I think the opposite.
You think the opposite.
Yeah.
Okay. Okay. So you go.
I think the same as Jen.
You think the same as Jen.
Me too.
Who is meet you?
Tiffany. Right here.
Tiffany.
I also agree
With who?
with the pink group.
With the pink one?
Yeah.
And you're Anna, right?
Yes.
I think it's the pink one too.
You go with the pink one too? Yes, girls.
I agree with the pink group too.
You go with the pink too. Okay.
I'll go with pink too.
I go with pink as well.
You go with pink as well.
Mm-hmm.
Yes, Alicia and Alexandra. What do you think?
Pink.
Pink.
You go pink as well?
Pink.
Okay.
I said pink too.
You said pink too? Oh, okay. Sorry about that. Okay. Marianne. Dr. Thomas. Okay, so Dr. Thomas is not here. And that costs. Okay, girls. Now, all of you who voted pink, all of you who voted pink should apologize to Dr. Shack. Why? Because Dr. Shack was the only one who got it right. So the pink team lost. And why? The main thing that's going to just cause a greater attenuation. As here. And we can say it's a lower attenuation here. Is because in this blue muscle here is what's going to happen on our blue. What mainly happens here is that there's going to be a greater reflection. Whereas here is there will be a weaker reflection. Did that make sense? Just look at it, just look at A. What happens? Don't get the way out of it. Sound wave hits something that runs like this. So yes, more energy is going to get reflected back. It's just like walking, yes, you're running into a wall. Whereas here you say, well, I'm coming across something that runs like this. And yes, I'm like this. So yes, it will produce a reflection, but that reflection is going to be weaker. Because here is it experiences less resistance. So yes, Dr. Brown, all these girls here is they owe you. You set the price that they gotta pay. Thumbs up? No, you set the price and let's get it fixed right here.
I don't know what the price will be.
Well, you won, so I can set the price and you say, I don't need that.
I think about it.
You think about it, okay. Oh, that's a mean look. Because yeah, I'm going to get these girls now. Okay, girls, but that's the explanation behind it. Okay, so mainly you can say it's mainly because that's the sound wave that's will be running against that's up alongside that's the muscle fiber. It experiences a lesser resistance in this case here. And that's going to cause a lesser amount of energy being sent back, which will mean that will be lesser attenuation. There's we go bam like this. It'll be a greater reflection. That greater reflection will cause more attenuation. Although it was the same kind of muscle. Okay, we didn't say skeletal muscle versus cardiac muscle, skeletal muscle versus smooth muscle, skeletal muscle versus that muscle, blah, 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 blah. They were both skeletal muscle. They could both be skeletal smooth muscle. They could both be cardiac muscles. That's not the point here. The relation between is okay, the fibers or filaments of that muscle to yes, okay, the direction in which the sound beam hits them. Did you girls get that? Beside that, just okay, just remember your list or table. So water, body fluids, fats, soft tissue in the middle. Okay. Then we got muscle, then we got bone and lungs, and then ear. Clear? Okay, girls. And I guess I'll see you ladies after you had your lunch. Your energy level has attenuated quite a bit. Okay, so I see you girls, should we say it's okay at 1:05? Good. Have fun till then. Yes, girls, welcome back. Any questions? About attenuation and attenuation coefficient? Good. And as I said today, earlier this morning, okay, it's another way in which yes, okay, attenuation can be yes, okay, discussed, or you can say it's okay, simplified. Is going to be yes, okay, in terms of what we call the half value layer thickness. Okay. And we can say, okay, this is again, yes, okay, that's going to be yes, okay, way to, you can say it's okay, quantify how much yes, okay, a sound wave may attenuate. Now, mainly as okay, yes, okay, we can say it's okay, differentiate this one here from yes, okay, what we earlier called yes, okay, attenuation coefficient. I mean, yes, okay, break down this word into two parts. Now, word, that's okay. Where it's going to be half value, and the other one is going to be yes, okay, layer thickness. Okay. Now, okay. Now, when it comes to yes, okay, defining yes, okay, what our value layer thickness is going to be, we can say it's okay, it is the distance. Or in terms of ultrasound, we can say it's okay, when you say distance, it's okay, it will be yes, okay, the depth. Okay. at which and now comes just okay what we mean by the half value, that the sound wave, or you can say sound attenuates to half of its initial value. Did that make sense? So what is going to be as okay, or half value thickness, we can say as okay. If this is, for instance, okay, is our image. The half value layer thickness is mean is okay, going to be at what distance or at what depth, which is okay will be as okay expressed in, we can say it's okay, centimeters. Is it that the intensity of the sound wave that started a journey here has attenuated to half of the initial value? That distance will be referred to as the half value layer thickness. Did you girls get that? So if yes, okay, just as okay, compare this versus yes, okay, what we call, you can say it's okay. Attenuation coefficient. Whereas okay, an attenuation coefficient, we mainly say that okay, yes. The distance was fixed as 1 centimeter. And it was made as okay, just because it's okay, based on the varying amount of lesser or greater attenuation, that okay, your overall attenuation coefficient will either be greater or less. Whereas if you look at your attenuation of half value layer thickness, in this case here, yes, okay, you can actually say, okay, the amount of attenuation that we are talking about, that is fixed as half of the initial value of any of the 3 bigness parameters, whether that is the power, amplitude, or intensity. Okay, so the distance that it traveled to, which is okay, the power is reduced to half the initial, the intensity is reduced to half the initial, or the amplitude is reduced to half of the initial. That distance will be called the half value layer thickness. But here's okay, the half value means says okay that sound is going to attenuate to half the initial value. Okay, what is that going to be? Depth here is okay, that depth is made as okay, going to be referred to as layer thickness. Because you can make it says okay, the greater or lesser this depth here is going to be, okay, because okay, this would be a lesser layer thickness. This here, no, yes, okay, a greater layer thickness. Did you girls, or did that make any sense? So here is okay, the actual thing that we are looking for is at what depth does a sound attenuate to half its initial value? Did you girls get that? Okay. Now, we can look at that and say, okay, okay. So do any of you mind if I just go to another slide? No, before I do that, so girls, just remember, girls, that this phrase here, that a sound wave attenuates to half its initial value. Okay. This can also, yes, okay, be replaced by the phrase that it attenuates by 3 decibels. Now, as I said, as I said yesterday, once you see the word attenuates, that automatically means that's okay, reduce. Reduction in what? Power, intensity, and amplitude. It means that's okay, gives this here is okay, the negative value. So that's okay, we can say it's okay that your half value layer thickness can also be as okay that it's going to be the distance or the depth at which the sound wave will attenuate by 3 decibels. Right? Because what does this attenuate by 3 decibels mean? That, okay, yes, it is reduced to half the initial intensity. If you guys remember the table that we made, we said minus 3 decibels means that, okay, yes, these 3 bigness parameters, yes, okay, reduced to half. So if you find this, okay, had a sound wave which had, okay, as an initial power of, let's say, as okay, 20 watts. When it decreases by 3 decibels or attenuates by 3 decibels, or there's a change of minus 3 decibels in this initial power, that may mean that, okay, it's going to be halved. Which means that, okay, yes, there will be, as okay, a power of 10 watts. Clear? Okay. So just as okay, a different way in which it's okay, your half value layer thickness can be defined. Okay, the pink star are the same. It's the distance at which yes, okay, the sound wave is okay, not actually it's just okay, half its initial value, but actually it's okay, attenuates by 3 decibels. Where the word attenuate directly mean that okay, yes, it's going to be negative. What negative causes it to become? A fraction. Clear? So that's okay, minus 3 becomes half. Just give me a second, girls. Did you girls get that? Okay. So practically, yes, okay, it means the same. It means the same. Okay. Now, mainly, yes, okay, what you're achieving, half angular thickness is going to be expressed in, is going to, yes, okay, be asking us, okay, what is the distance at which, yes, okay, as sound waves, power, intensity, or amplitude is reduced to the half. Okay, so it's going to be as okay, all be about as okay, what is this distance? How many centimeters is it? Here, where okay, as here this factor is constant. And your attenuation coefficient, it was opposite. It was as okay, in a fixed distance or in a constant distance of 1 centimeter, how much attenuation did we have? Okay, so this is mainly as okay, just you can say as okay, the complete opposite of attenuation coefficient. And here's okay, we keep the distance fixed. Oh, sorry, we keep the degree of attenuation fixed. And say, okay, at what distance is that's going to occur? Did you girls get that? Yes, girls, did you girls get that?
Yes.
Yeah.
Okay. Anybody who is in doubt? Okay. Now, ladies, we can then say, yes, okay, now what is going to be, yes, okay, the relationship of, we can just, okay, say, the half value layer thickness versus, we can say it's okay, attenuation coefficient. And what we mainly as okay just will do is as okay relate both of these two areas okay to frequency. Now what we mainly can say is if we have a great half value layer thickness, that's mainly going to be because okay we may have a low attenuation coefficient. And what is going to give us okay as a low attenuation coefficient? A low frequency transducer. Whereas, okay, as on the other hand, what do we see is that we have a low half value layer thickness. That can mainly be because, okay, we have a greater attenuation coefficient. And why is it that we may have a greater attenuation coefficient? Mainly because, okay, we may be using a high frequency transducer. Is that clear? Now, what was it that our attenuation half value layer coefficient meant? Practically, yes, okay, if you look at it. Okay, we can say it's okay, we have two transducers, or we have a transducer. And just let's, okay, yes, okay, let's just look at just one of the three bigness parameters, because we know when one increase, the two others will also increase. When one decrease, the two others will also decrease. So just to make it simple, we can say, okay, we look at the power. Now we can mainly say, okay, this transducer here may have, okay, as a power of, let's say, as okay, 20 watts. Our question then comes as, okay, what is going to be as, okay, our half value layer thickness? Now the main criteria that's going to is okay, we as okay valid here to explain the half value layer thickness is going to be. At what depth? Is it that this 20 watt initial power here is going to become half, which is going to be as okay, a total of 10 watts. Let us just say it goes that, okay, as that happened at a depth of 5 centimeters. Yep. So in this case, here's okay, our half value layer thickness would have been 5 centimeters. Because that was the depth at which is okay, this 20 watt pulse wave here is okay, attenuated to half of your initial power, which is going to be 10 watts. Clear? We can just look at, okay, as another example. I mean, yes, okay, just to keep it simple, we say, yes, okay, it is the same power of 20 watts. Clear? Well, let us just assume that, okay, the only thing that we want to is, okay, talk about here to determine the half value thicknesses and what depth is it that is going to is, okay, decrease from 20 watts to 10 watts. Let's say here, okay, that happens here. Let's say it's okay that at a depth of just 2 centimeters. Did you girls get that? So here is okay. That 20 watt, a power of 20 watt is okay, attenuated to half at a shallower depth, which was 2 centimeters, which in this case is okay, then just say it's okay. This is a shallower half value layer thickness, because at a shallower depth, or at a depth, or at a layer thickness which was lesser than what we had over here, which was 5 centimeters. That 20 watt power attenuate to half 10. And likewise here. Did you girls get that? Did you
Yeah.
girls get that?
Yes.
Okay. Now, when we then just look at these, yes, okay, two examples, and we can ask, okay, mean, yes, okay, say, well, okay, A and B. You can mainly say that, okay, ladies, if in this case, yes, okay, in A, the power of 20 watts attenuated to a half at a depth of 5 centimeters. We had a greater power as okay. We have a greater half value layer thickness. Because half value layer thickness means says okay, here it was 5 centimeters, whereas here is okay, it was 2 centimeters. But if you look at it here, we can mainly says, okay, well, what happened? The power is okay, attenuated to half at a shallower depth, which mainly is okay, causes that this one here is going to have okay as, or we can say okay, B has a greater attenuation coefficient compared to A, which has a lower attenuation coefficient. Because if it, you can say it's okay that it decreases from 20 watts to 10 watts at a distance of 5 centimeters, you can maybe say, like, roughly speaking, you can say that per centimeter. Here it's okay, it's going to be it's okay, roughly, it's okay, 2 watts per centimeter is going to attenuate, right? Where the whole area, you can roughly see it's okay, there's going to be it's okay, an attenuation of 5 watts per centimeter is going to attenuate by 5 watts per centimeter. So here is okay, you have okay as a lower attenuation coefficient, which gave you a higher value layer thickness. Contrast to over here in B, where okay, as it attenuates to half at a shallower distance with mainly or meter, okay, as you will have a greater attenuation coefficient. Did that make sense? Where we mainly can say, as okay, what might have caused us, okay, this lesser half, that's okay, greater half value layer thickness in A and a lower attenuation coefficient in A versus that's okay, lesser half value layer thickness in B and a greater attenuation coefficient in B. And mainly be because okay, this transducer here had a high frequency. And okay, yes, this is okay. Because it's okay. This other one here is okay, would have had a low frequency. Or just as okay, not to confuse the colors, we can mainly say okay. We can say that okay, yes. In A, what did we have? There was quadruple mainly as okay, because as okay, we had a low frequency, where in B is okay, there was mainly as okay, because we had a great frequency. Did you girls get that? Okay. Or yes, okay, as we said earlier, 2 girls start with the same amount of money. $2,000, right? Or $5,000. One girl only spends $20 per shop. Contra to the other spending $200 per shop. What will happen? That girl who only spent $20 per shop will be able to just, okay, go for, I guess, okay, to more shops because before, that's okay, her amount of money reached from $200 to just $100, right? She was going to be able to go and shop in up to, yes, okay, 50 shops. Contra to the one that spends just, okay, $200 per shop. So that's okay. The more a sound attenuate, the greater will be as okay the attenuation coefficient. But the greater the attenuation coefficient, the lesser will be the half value thickness. And vice versa. The lower your attenuation coefficient, because of a lower frequency, the greater will be your half value thickness. Because it will be able to travel to a greater distance before it pops. Did you girls get that? So that's okay. These relationships here, that's okay, are important. Okay. The E is okay. An easy way to remember it is attenuation coefficient is inversely proportional to the half value layer thickness. Now, since attenuation coefficient is directly proportional to frequency, frequency is going to be inversely proportional to your half value layer thickness. Does anybody have any questions? Okay, girls. Now, at the bottom of the table on page 87, where it talks about as okay, half value layer thickness, you may see that okay, there's something written as synonyms. These terms here, yes, okay, you need to remember. And it is going to become, yes, okay, a common practice in following chapters that you may see that, okay, yes, something is going to go under more than one name. So your half value layer thickness can also be referred to as the penetration depth. If you just look at it as I said earlier, the depth at which it's okay, a sound is going to be able to penetrate. What's going to happen at that depth? Well, okay, that's when it's going to just okay have attenuated to half. Did you guys get that? Right?
Yes.
Yes.
Okay. It may also be called as okay, depth of penetration. Yes, okay, just holding, yes, okay, this year like this, contrary to exactly what it was in the previous one, right? And last one is okay, half boundary layer. So all these are mainly as okay, as I just were referred to them as being nicknames, or what we commonly as okay were referred to as okay the half value thickness. Okay, so you may, and why did they put these terms here? Mainly because okay, you may be asked a question about half value layer thickness, but they may not use the term half value layer thickness. They may just say, what is the depth of penetration? What is the penetration depth? Or what is the half boundary value? Did that make sense?
Yes.
Okay. So that's one of the things that okay, yes, makes, you can say it's okay, your SPI boards a little bit difficult, because they may not use the traditional term, which is written at the top of each topic when they ask a question. So all these synonyms or nicknames here, yes, okay, for different things, yes, okay, you have to remember them. Did you guys get that? Any questions? Anybody want to say something? Okay, girlies. So if we just take B, and I say, well, okay, yes, if you, for instance, okay, increase the initial power from 20 watts to, let's say, it's okay, 200 watts. What do you think the half value layer thickness will be then? Just so you know that, okay, yes, the half value thickness is mean is okay, going to be that, okay, yes, these 200 watts, yes, okay, becomes 100 watts. Well, what do you think will be the distance?
$50 watts? No, that's the distance, 50 centimeters.
No, my dear, for B. Here, the average, okay, happened at 2 centimeters, right? So if everything, yes, okay, everything, yes, okay. If it was the same, but the only thing that we changed is the power from 20 watts to 200 watts. At what distance do you think it is going to, yes, okay, reduce to half?
20 centimeters.
Who was that?
Haley.
Exactly, my dear. So here's okay, we can make it says okay that the half area thickness would have been 20 centimeters. Clear, where we can still say it's okay, well, okay. In both cases, okay, whether it was here or here, it's okay. The attenuation coefficient still was the same. Clear? It remained the same. So did the frequency. Mainly because, okay, the frequency remained the same, attenuation coefficient remained the same, but mainly because, okay, we increased the initial power. Now I got to travel, yes, okay, at greater distance. So yes, okay, attenuate height off. And that distance could roughly, as okay, in this case, that could be 20 centimeters. Now the problem isn't going to be as okay, transducer is going to as okay, be able to send a sound wave all the way to a 20 centimeter depth. Okay. So that's okay, that's the limitations. But anyways. Okay. But the main thing here goes is the relationships between attenuation coefficient and half area thickness. The relationship between half area thickness and frequency. Half area thickness and, okay, let me say total attenuation. Okay. Because you can say it's okay. In both cases, that's okay where there was attenuation coefficient or half area thickness. The changing factor could be as okay, or the common changing factor could be as okay, the frequency. In your attenuation coefficient, the distance was fixed at 1 centimeter. And your half area thickness remains okay. Then what is the distance? Okay. There, okay, as an attenuation coefficient, we say, okay, how much attenuation is it that a sound wave undergoes at a fixed distance? Whereas in half area thickness, we say, what is the distance at which a sound wave undergoes as okay, a fixed amount of attenuation, which is going to be half the initial. So attenuation coefficient is directly proportional to attenuation, which makes it directly proportional to frequency. Half angular thickness is inversely proportional to total attenuation. Hence, hence inversely proportional to attenuation coefficient, and hence inversely proportional to frequency. Did you ladies get that?
Yes.
Any last questions? Yes, girlies, any last questions?
No.
Yes, Astrid, do you have any questions, my dear?
No, I don't.
You good? Who else? Yes, Alicia, do you have any questions, dear?
No, I don't have any questions.
Okay. Are you good about the relationships?
A little bit. I definitely have to go over them more.
Yes, Dr. Marissa, what about you, my dear? You
I'm
good?
good. Yep.
Good, good. Dr. King,
Yeah,
good?
kinda. I have to reread.
Kind of?
Yeah. I'll go over it
Why just kind of?
because
Because what?
this is learning something.
Okay,
So-
no offense.
Okay.
Well, let me put it this way. Yes, okay, you girls are probably, yes, okay, the girls that are going at the slowest pace doing physics. And all my other badges, at this time, we will probably, as okay, already have been at chapter 8 or 9. Okay. Dr. Dixon, you good?
Yes, I'm fine, thank you.
You're fine. Okay, good. Okay, go. So that's okay. Those of you who say kind of or whatever. What is it that you still have doubts about? I think is okay. That's your weakest point.
What we just went over with the half
Half.
relations.
Okay, listen, girls. I usually give this example here. Let's say it's okay, we have 2 vehicles. Have any of you seen those small vehicles where it's okay, if somebody sits in it, they can hardly fit a bag of tomatoes?
Yes.
Yeah.
And then we say it's okay, we may have okay as a big pickup truck, right? Now what we can mainly do is just okay, we can fill up this car here with, let's just say it's okay, let's just assume that they both take, yes, okay, 20 gallons. Clear? Now, what is going to be as okay your half value layer thickness? That's mainly as okay going to be the distance that both of these car here, vehicles here, is okay, will be able to travel. And at which is okay, the amount of gas in their tank is going to remain at 10 gallons. So mainly because okay, that butter bin size car yes, okay, uses less gallon or less gas per mile. Which mainly we can say it's okay, mainly is that okay, yes, it has a low attenuation coefficient. Will be able to just okay travel a great distance before is okay, the amount of gas available is okay, left in the tank when we start off with 20 gallons. And then with 10 gallons, it's going to be able to travel a greater distance. Which means we mean that, okay, as that half value layer thickness in this case is going to be great. Whereas for this, which means okay, not just burn gas, but actually swallows it. What do we have? We actually have okay as a it's at a lower distance that it traveled before as okay using a total volume of okay as 10 gallons of gas. Which means this one here is going to have okay a low value layer, a low half value layer thickness. Because it travels okay a small distance, which mainly means that okay as it uses more gas per mile. Okay, you could say the distances echo had been as okay 100 miles. Whereas okay here this distance would only had been as okay as 10 miles. Clear? So why do they have okay as a great attenuation coefficient? Mainly because okay, here this car here is okay used. Is okay 1 gallon per mile. Where here is okay, it used 1/10 of a gallon per mile. Did that make sense?
Yeah.
So you can read as okay, since this here was okay, so that's okay. Comparing the size, you can say that this one here had was okay, just like okay, talking of a great frequency transducer versus a small frequency transducer. Or you can go and say is okay, you're shopping. Less amount of money per shop that comes after is okay, where you're going to go into a shop every mile. Versus okay, uses a greater amount of money per shop. And okay, in both cases, okay, you start off at the same amount, but it's okay here. Only shopping at 2 shops before is okay. The amount half is okay. Is halved, but is okay. You may be able to shop at 20 shops before it's okay. You spend half of the money that you start off with. If not, just as okay, make a spreadsheet like this. The half value thickness, attenuation coefficient, and frequency. Where blue goes with blue goes with blue. Red goes red goes red. That's probably as okay, you can say it's okay, the easiest way of doing it. This goes with this, like this. This goes with this, this. So if you compare something where arrow goes down and arrow go down, that's because they're inversely proportional. Because arrow goes up, arrows goes up. Maybe you say, okay, let me compare this with this. Okay, arrow goes up, here it goes down, inversely proportional. Here it goes down, here it goes up, inversely proportional. Likewise here, red down, red up, green up, green down. That makes this and this inversely proportional. Mainly because it was also inversely proportional to this. Where this and this here is okay, we're directly proportional. That makes sense. So only then is it going to just okay pay off if you make an index card like that and put it on a place that you look at several times a day. It can be on your refrigerator as okay, your dressing mirror or whatever. If you are one who has okay frequently go and visit that's okay the refrigerator, put it on the refrigerator door. If you are one of those who stand in front of the mirror for long periods of time, combing your hair, applying mascara, lipstick, and all that, then put it there. Because as you put on your lipstick, you may be looking at these relationships here. So yes, okay, your dressing table mirror may, yes, okay, look like, okay, as the book of ultrasound physics. Or your refrigerator. Okay. It after all will be better than, okay, as looking at, okay, as your UI bill. The mortgage bill. Not things like that. Okay, girls? So that's how you can prepare. And just get it straight, ladies. This is not something that you will get by us, okay, reading it once. Read it over again and again and again and again and again. And as we go through the book, you will see as okay that there's something is okay, which previously is okay, used to be hard to understand, but it will start make more sense as we proceed. Okay. Okay, girls, I went over a little bit, but see you ladies tomorrow.
You mean Thursday?
Oh, sorry, Thursday. Okay, thank you. Yeah,
Okay.
sorry for that. So see you ladies on Thursday. Okay.
Thank
Okay.
you.
Bye.
Okay. Have a blessed day there. Okay. Bye, girls.